Correct. Usually, what designates that a triangle is right? A square in the corner. So, if I put that there, then you have parts of said triangle. What is one part that never changes in a right triangle? The hypotenuse. I should rephrase that. The location of one segment never changes. The hypotenuse. The hypotenuse is always located opposite the right angle. And then it stems from the other sides. The other sides of a right triangle are always called legs. We call them other things when we place a theta into it. Okay. From what I understand, Sev introduced you guys to using theta.
Yeah.
I know that just means an angle.
Okay, I wasn't judging.
Okay. If you put it, theta is just an angle. It just stands for an angle. I know that I use x in regular geometry before. It's just, hey, pick an angle, whatever. So if I place an angle, I call that theta. Theta is kind of like a circle with a line through it. That's all it is. It's just another way. It's a different way to represent an angle. That's all. Yeah. Angles always look at their sides opposite. Remember that? Angles always look at their sides opposite, which makes the other side near adjacent. Now, I always taught trigonometry as perspective. It depends upon where you are in a triangle to what sides are opposite you and all that other stuff. Because if I place my theta here, I'm no longer looking at an adjacent, I'm now looking at an opposite. So depending upon which angle you're at, depends upon which sides you're looking at. And you guys remember that from last year, right? Which stems then to be able to do this. Chief Sokoto, the proud Indian tribe. Probably don't need to do that, but anyway, what did SOHCAHTOA stand for? Besides standing for trig and the American dream. What do we got?
Sine, cosine,
So this should stand for sine of an angle is your opposite over the hypotenuse. Cosine of an angle is your adjacent over the hypotenuse. And tangent of an angle is your opposite over adjacent. Good old-fashioned SOHCAHTOA. What we do here in Algebra 2 then is introduce you guys to the inverse trig functions. We talked about, we've mentioned them before, but what I want you guys to remember, if you're looking at inverse trig functions, how do you find an inverse of a number? What do you do to it? You flip it. So basically what happens here, if we work with what are the inverse trig functions, I flip this, I get hypotenuse over opposite. I get hypotenuse over adjacent, and I get adjacent over opposite. That's if you flip them, but then they have new names. It's no longer sine, cosine. That's how you find an angle. That's how you undo a sine to find the angle. It's the inverse operation, but the inverse of the trig function is different. The inverse trig functions are called cosecant, secant, and cotangent. Cosecant, CSC, is what we use for that. Secant is SEC, and then cotangent is COT. The reason that we have these is because later on in, it'll be after, well after spring break when we get to it, we will eventually be graphing these things. And a regular sine graph would look like this. It starts at 0, goes to 1, goes to 0, back to -1, back to 0. So you start to think about, if sine is opposite over hypotenuse and that equals 0, the inverse of that would be something over 0. Can you divide by 0 though? No. That's why you wind up with what are called asymptotes here, here, and here. What's the inverse of 1? 1. What's the inverse of -1? -1. What's the inverse of a half? What's the inverse of a half? -half. So inverse trig functions flip from trig functions. And we go through all the process of how to do all of this later on. And you'll be able to graph something that looks like this. With no problem. All right, we'll be able to do all that without any real struggle because we'll understand where do all these values, these critical values come from. And we'll be able to plot those rather quickly, and then you'll know that, hey, cosec is just the inverse of sine. So if sine's going up, it's swirling around, it just blows up. The curves just blow up. That's all they do. Okay? That's why we show you guys in Algebra 2 inverse trig functions. Okay? Not so bad? We're getting there. Okay? Oh, I remember. Do you remember? Okay. Yeah, and that's what Seb did a lot. He did the Q root 2, and all that. He uses Q's a lot of those for those. I used X's, and it doesn't matter how you set them up. So what we're dealing with here then, all right, is we're going to look at the two special right triangles. We're just kind of doing a quick overview to see if you remember how to set them up. These will come back into play a lot more later on because that's the whole basis of all this, is working with these. So if you've got a 45, 45, 90 triangle, remember that came from what object? How did we create that? Half a square, good. Since we had half a square, that's where we knew that our sides were always the same. Diagonals in a square bisected the 90, and that's where you got 45s. Plus, if these were an isosceles triangle, that means base angles have to be the same, and that's where you get your 45s. Now, one thing you found is that no matter what side length you chose for the square, this was 3, this had to be 3. So what's 3 squared plus 3 squared? Square root of 18 was 3 root 2. And it always had that pattern going through, where you had something, something, something root 2. And I know Seb used it in terms of Q's. I always write it in terms of X. Then I'll explain to you guys my reasoning behind that here in a second. So we always have these as something, something, and something times the square root of 2. And it was the same basic idea for the 30, 60, 90 triangle. What shape did that come from? Don't say just a triangle. No. No. What? What? They came from a triangle. What kind of a triangle? That one.
I know what it is, but I can't. No, it's like where you, like two sides are the same.
If this is an equilateral triangle, what do you know about all the sides?
All the same.
What do you know about all the angles? When you draw the altitude, you get the perpendicular bisector of the side. So if this whole thing was 2, that means this was a 1. This is a 30. 1 squared. Well, what's 2 squared? What's 4 minus 1? What's the square root of 3? The square root of 3. So in the 30, 60, 90 triangle, that's where you had your pattern of 1, root 3, and 2. And this is how I always write this out. Do you guys agree that angles always look at the sides opposite? Yeah. So why I draw these arrows here, that means that my 30-degree angle is looking at the side opposite. The value of the side opposite of the 30-degree angle is 1. That's why I called it x. The 60 looks at the x times the square root of 3. And the 90 looked at 2 times x. The reason I write out this, what I called an algebra jig, was that no matter what side length you knew in the triangle, you could then solve a one-step equation to figure out what that common multiplier was and substitute into everything else. For example, if I had a 30, 60, 90 triangle and I knew that across from my 90 was 18. Exactly, in my head that means that, oh, I know that this part equals the 18, so x has to be 9, which means everywhere else I just put a 9 in value of the x. And that's how that works. Obviously, it's not always going to be that easy. You'll have a lot of rationalizing. Oh, you're not doing that. They do. Do you like radicals in the denominator? Neither do I.
Oh, that stuff.
That stuff. It comes back real quick, because a lot of these things, when we start working with inverse properties, you see how there's a specific pattern that happens. It's very quick. Okay? All right. This is where this stuff came from. And I know you guys have all seen this, and like I said, this is a quick little, what you did last year in trig in about 5 weeks, we do in about 2 days, and then we go into law of science stuff. But one thing I want to show you guys is how the 6 trig functions, this would be a good one, the 6 trig functions come into play for the special triangles. Might not be a bad idea, okay? Might not be a bad idea. To be honest with you, these 3 angles are the ones that are going to do everything once we get rid of our calculators. But what I want to show you guys is how we set this stuff up, no matter what angle measures or what things we're given, and how we can find inverses and things like that. Excuse me. What I usually do first of all when I'm looking at these special triangles, I just draw them off to the side real quick. And I do that. And I leave them as 1s, root 3s and 2s, and knowing that if I have to do a multiplier, I can. Okay. So when I start there and I look at a 30-degree angle and I want to find its sine, sine is what over what? What's opposite the 30? 1 over 2, which means the sine of 30 degrees is 1/2.
Can you say that one more time?
That one more time.
Can you say what you just said?
I'm messing with this, I'm sorry. So if I'm at the 30 degrees, what's my opposite?
1.
1. What's my hypotenuse?
It's 2.
2. So the sine of 30 is 1/2. 1 over 2.
Could we write it as x over? Wait, why 2? Oh, 2 times.
Yeah. I got rid of the x values, because if I have 1x and 2x, if I take 1x over 2x, I get 1/2. Because it will always go, that value of x will always simplify out into being 1 root 3 and 2. No matter what whatever that multiplier is. No matter what, it'll always work out. Okay. What's that, Hopmore?
I said, I was asking if you wanted us to copy the triangles, but then it's.
Oh, okay. It's a good thing to have. I also know that in pre-calc, a lot of times, we've been known to give this as a times test, because it is the building block of all trigonometry. Just like I gave you guys that 12 by 12, what do you call it? Actual times table thing. Yes, ma'am?
Do you want us to put 1s for that, or
Yes.
just x?
1s, because it's easier. Because, like I was just saying, that if this was an x, 1x over 2x, what does that simplify to be? Exactly. It doesn't matter what the numbers are, it's always going to simplify to be 1/2. Cosine. What's the adjacent to 30? The root 3. What's the hypotenuse? 2. There we go. Tangent. Remember, tangent, we probably should write this down in case you guys forgot. So, So if I do all that, the tangent at 30 is going to be the opposite over adjacent. What's the opposite of 30? 1. What's the adjacent?
Wait, which triangle are you doing this for?
I'm looking at the 30.
But which triangle?
Which one has the 30?
Oh, okay. Yeah.
So I get this 1 over root 3, but is that good?
No.
What is it in terms of good? Very good. This would equal root 3 over 3. Everybody okay with me on that? All right. Shh, ladies, come on. Same thing over. How's that being racist? And I said, shh, ladies. Oh. What's the inverse then of 1/2? 2. Because cosecant is the inverse of sine, which means that this would be hypotenuse over adjacent. Well, it's 2 over 1, so it's 2. The secant would be hypotenuse over adjacent, so it would be 2 over root 3, which is 2 root 3 over 3 when you rationalize. And then I go back to my cotangent. Cotangent is going to be the inverse of tangent. Well, before I rationalized tangent, I had it written as 1 over root 3. If I flip that, I get root 3 over 1. So what's the cotangent of 30? Root 3. Okay? And I do the same thing with 60s. When I go to a 60-degree angle, my opposites and my hypotenuse never change, but my opposites and adjacents flip-flop. So now, what's opposite of 60? Root 3. Opposite my 60 now is the root 3. Hypotenuse didn't change. Adjacent to my 60 is now a 1, so I get the 1/2. And then my tangent is my opposite over the adjacent, and that's where I just get the plain old root 3 again. So, what's the inverse of root 3 over 2? You just did this. 2 root 3 over 3. What's the inverse of 1/2? 2. And what was the inverse of root 3? Very good. It would have been 1 over root 3, which would be root 3 over 3.
And if we were to add the x's back, would it just be multiplied by those?
Yeah, and then the values, and because that value of x would just be simplified out as you do all those fractions. Okay. A lot of times, this is more important than anything with having to worry about any values of x. Because if you know where you are as we get to the unit circle, it all boils back to knowing these. Of understanding what the relationship, how did you get a 1/2, that kind of thing.
So like, if we're doing like the sine of 30 and you put 7 in, it would be 7 over 14.
Yeah.
That's the ones.
Yep, that's all there is. That's exactly it. Because no matter what, it will always simplify to be that ratio. And that's why they're important. Switch gears to 45. What's opposite either 45? Yeah, you're going to get 1 over root 2 for both sine and for cosine. So that rationalizes out to be what again? Yeah. Both of them become root 2 over 2. What's the tangent of 45? 1. So then you start thinking about your, what do you call them? The inverses. If I go back to the idea before we rationalize this, the sine of a 45 was 1 over root 2, which means the cosecant, the inverse, would have been root 2 over 1. Which means the secant would also be root 2. Oops. And then last but not least, what's the inverse of 1? 1. And this little table set up like this is something that I know that Miss Denny uses all the time. All the time. Okay? You will see this a lot. And we use it, I know that I use this a bunch also in regular pre-calc as well, because if you can draw these two triangles, you're going to understand where every single piece of this comes from, because it's just a special right triangle, and you guys all know this, I hope, which means eventually, in the next week or two, you'll be able to figure out all of that. Yes, ma'am.
Why is root 5 sine and cosine was over 2?
What happens here is if you look at the original, well, yeah, you left your poster. Is your poster still right there? I forgot to move it. What happens here is, no matter where you are, LeBlanc, if you're here, your opposite is 1 over root 2. Your adjacent is 1 over root 2. So that you get the same values because it's isosceles. So if it's 1 over root 2, when you rationalize that, you multiply top and bottom by root 2, and that's where you get that root 2 over 2. Okay? Is that vaguely somewhat a little bit of here? You'll get used to the inverse stuff here.
I know, it's just
It gets quicker, believe me. A little practice and you guys will fly right through it. Okay? And I'm usually right. I don't need to do this one. Hey, what do you do when it says solve a triangle?
you solve the triangle.
All the pieces. What's that? Nothing fun. Right? Yes, sir.
You find the angle measures and you find the side.
So what happens here is that you're going to use trig to find your missing side lengths and angles and things like that.
But you can't use a special right triangle thing when you shoot.
Correct. Which means you have to go back to good old-fashioned SOHCAHTOA. So one of the things to remind you guys of is that when you have right triangles, if they're labeling them out, if they label them out with capital letters, lowercase letters are always the opposite. So big A is always looking at little a, big B is always looking at little b, big C is always looking at little c. That's where those things come from. And I know this is how it was in geometry as well, just today's a lot of reminders and things like that. One thing that I will try to beat you guys over the head with is never use anything you solved for. Always reuse given information. Okay? Because if you solve something and it's wrong and you reuse a wrong piece, will you ever be right the next time? No. But with trig, if you reuse givens, you get a fair shot each and every time. That's one of the main reasons why I want to make sure that you guys always reuse givens. So in this case here, my triangle is awful.
The angle you're always going to use is A.
It depends on what they give you. All right,
Well, because for this case.
in this case, yeah. In this one here, they tell you this is 20, this is 12. So if I'm at my 20-degree angle and I'm looking at A, 12 is, yes ma'am.
Wait, can we still use SOHCAHTOA for it though?
Yeah, that's what I'm getting at. What is 12 in relationship to the 20? The opposite, good. So that means I have an opposite, I have to find an adjacent, and a hypotenuse. What trig function am I going to use for an opposite to find its hypotenuse? Sine. Sine, the sine of 20 is my opposite over my hypotenuse. So my unknown value here is in my denominator, which means I'm going to ask if you remember how to do this. True or false? True. Okay? True or false? True. It's true. Okay? Try one more. True or false? It's true. Notice, all I'm doing is changing things on diagonals. Whenever you have fraction equal fraction, that just means it's a ratio. Trig values, all this trig stuff, these are all ratios. Because if I put this over 1, does it change anything? No. So that means that anytime I'm trying to solve for missing values, a lot of times I can switch something along a diagonal to solve for x quicker. You're going to hear me say this a ton. In order to change this, I exchange-o. Shut up, it makes sense. If I exchange them along the diagonal, I get the hypotenuse will equal 12 over the sine of 20. Now, we haven't had to do this to make sure we are all in the right mode. We need to have our calculators in what mode do you think? In math mode. That's smart, yes. And you're calculating, yeah, if you turn on the calculators, when you press the button that says, I don't know, mode, you want to make sure that you are, for right now, highlighted in degrees. We are not in radians yet. We haven't gone rad. We will show, we have a great movie for you to show. Hit the button that says mode, and then you want to make sure your calculator is highlighted in degrees. Now, a lot of times what I want you guys to make sure of is that whenever you're doing trig stuff, especially for the course of the next, come on guys, especially for the course of the next week or so, we're basically living and dying with the calculators for a lot of this. Whenever you turn the calculator on, please make sure you are in degree mode. LeBlanc, if your batteries ever fall out, no, I'm being serious. It'll reset itself. So you got to make sure you re-hit mode and make sure you put it back into degree mode, okay? The rest of you guys, I don't think it'll reset itself. The only thing that I can think of is that if the battery completely dies on you before you recharge, you might have to reset it. So always just hit the button and double check, make sure you're degree mode when you do this. Also, one little thing that I always want you guys to do with this trig stuff, I want you always to show me what you're going to put in your calculator before you put it in your calculator. The reason that I asked you to do that is because if you write down what you're going to do, you know what you're doing. If you press and you hit the wrong button with your thumb by mistake by going too fast, yeah. If you go too fast or something like that, you could easily make a dumb mistake and write down the wrong answer. Happens all the time. It happened on your testing on Friday. There were a couple people, I don't know if it's this hour or second hour, where they set up one of their equations and they had all the work written out correctly, but they typed in the wrong number. But they showed their work knowing what they were going to put in there. And I was able to backtrack to figure out what they did. They just mixed up like a 3 and a 2. They put them in different order. Yeah.
How come when you have it in degree mode, it's different?
Radians deal with the unit circle, which is within 2 pi. So it's putting pi in the answer. There's a whole other realm out there. So if you're in radian mode, and you hit the sine of 30 degrees in radian, your answer is going to be pi over 6. So if you put it in radian, hit sine of 30, you're going to get some crummy decimal. If you multiply that crummy decimal by 6, and you get 3.14159.
No.
Should have. Well, you're not. Are you in degree mode?
I'm in radian mode.
Huh.
Is this bouncing the wrong way? Sine 30 is pi over 6, sine 60 is pi over 3. Oh, you know what? I wonder if you have it.
No, she had like
-5.
-5, which is good. Why is it coming up that way? Don't worry about it. But anyway, that's where this will come to. We'll get to that later on. So when you do this, always round up to 2 decimal places. If you did this, what you guys get?
32.97.
3297?
Yeah, I got 35.6.
Okay, then I messed it up.
Oh, that's it.
Yeah, it should be what?
35.6 already.
09?
Yeah.
Okay.
We're mistaken.
Okay. And now, what I would do then is I would use, what trig function would I use then to find its adjacent? Tangent. The hypotenuse is 3509, right? Is that what you guys got?
Yep.
So if I'm using to find the adjacent, knowing my opposite, what trig function uses opposites and adjacents? Tangent. Again, your exchange-o, change-o.
This is the one I did before.
Oh, you put that one first?
Yeah.
So what'd you get for tangent then?
32.97.
32.97?
Yeah.
Okay. And now, how many degrees are in said triangle? 180. If you take out 90, what are you left with? Which means the two angles A and B are always going to be complementary. Which means the angle B has to equal 70. Now, I know that you guys probably could have flown through that real quick and say, hey, that's got to be 70 degrees, and you could have used angle B to find the other stuff. But what happens if you made a stupid mistake and you said it was 80? Then everything else would be wrong. Okay? It happens more than you would ever believe. What's up, Hopworth?
So for the final answer, would you want us to put like C, or C equals?
Yeah, and that's usually what it was. I left it as hypotenuse just to help you guys see what you were solving for, okay? Usually what happens, the easiest thing to do is to label out this circle, all right? Did Seb make you guys show what you're typing before you typed it? Or Gonzalez or Judkin or anybody? I know I always did.
I don't think we did that. Yes, I think we might.
They recommended that we just like.
I think 7.
It's,
I don't think it's
Highly recommended.
and to be honest with you, it's not that you need to, but it will make your life easier, okay? It makes your life easier.
Well, I don't know. I was just like, so would you consider like A equals B?
Yeah, and just, yeah, that's all, that's fine. We'll do that one tomorrow, but there was another version of this I wanted to show you real quick.
Just for everything else, because if you did, then you'd give you a partial quiz. So I'm like, there's no reason. What in the world? Like, see?
What do you do now? Oops. So, in this case here, what's the easiest? You guys are already yelling it. The way that you're going to solve for missing side length, if you know two of them, is what? Is it a 30, 60, 90?
Oh, I thought you could do like X, X, and X.
So you have to use a Pythagorean theorem. So this one is Pythagorean theorem one. In this case, to find the missing side length, little b, that's the opposite here, that's usually the first one we would find. So what we would do is little b squared plus 10 squared is 12 squared. What's 12 squared? 144. What's 10 squared? What's 144 minus 100? 44. I know it's been a while since we've had to use the calculator to figure out what the square root of 100 or what the square root of 44 is. It is. This one's an easy one. It's going to be 2 root 11. But do you know how to check using your graphing calculator? It doesn't rationalize. It doesn't do simplified radicals for you guys. But if you know how to, we did this back with polynomials. What you have, yeah, it'll be 2 over root 11. What you do is you go to your y equals. I know, but I'm showing how it always works. Why it works. So if you're not sure how to simplify a radical, if you go to y equals and you type in 44 divided by x squared, what the calculator is going to do, it's going to take the 44 and divide it by 1 squared, 2 squared, 3 squared, 4 squared. It's going to continue, it's going to look through all those values to figure out which one of those gives you a regular integer. And by going through the table, you'll figure out which is the largest one. So if I do that, if I look at the table, 44 divided by 1 squared is 44. 44 divided by 2 squared is 11. After that, it goes through all decimals. Okay? That means that once you get to this 2 and 11, your answer would be 2 root 11. And I know we talked about that when we did quadratics. That's how we were able to simplify those out. So you don't have to have the multi-view calculator. Actually, I won't let you use the multi-view calculator because it'll rationalize. These won't. So you'll have to know how to rationalize, just a little FYI. But I'll let you use this calculator to simplify your radicals if you have to. Okay? What's that? Rationalize, like 1 over root 2. You get root 2 over 2. Things like that. What do you do then if you have to find an angle?
Here's my angle.
Yeah, let's say you wanted to figure out what angle A was. Using your given information here, what would you use? What would you do to find angle A?
Opposite over adjacent or hypotenuse.
Well, I wouldn't use by adjacent because that wasn't given.
Right, so opposite.
Because what happens if I screwed up? Then you're screwed. So you always want to use what you're given. Okay. So when you do that, you would say the sine of A is 10 over 12. Now, whenever you're trying to find an angle, that's when you have to hit the inverse button, the -1 button. Remember that? In the calculator, you would do this. There's two ways that I like to show you guys. 10 divided by 12 and hit enter. That's with the fraction. So the sine of some angle is going to equal this crummy fraction. Second sine of my answer and hit enter. And that'll get you my A. Use the answer button. Second sine's the inverse. Whenever you're finding an angle, you're using the inverse button, the -1. And then you just of the answer of what you just typed in. There's many different ways to do it. That's the quickest way to do it.
This time we would like to dismiss those classes that have signed up to go to the gymnasium. Only those classes that have signed
That's
up
not us.
to the gymnasium.
The cafeteria.
Can we skip the cafeteria and go with the unhealthy?
No, we signed up for. They have it set up for.
Well, technically,
I didn't
signed
know.
up for that. We signed up for the.
You signed up for the suitcase thing.
What suitcase thing?
No, we signed up. Yeah, no, we signed up. Trivia, wax music.
Oh, they put us in whatever space there was.
I wish you just go back.
Can't. They told us no.
I just said, where do I lock?
Nope. Supposed to go right there. Guys, I'm not even done yet. Come on. Gives you an angle of 56.44. Do you have to put the degree symbol? No, I don't care.
Oh.
Just round it to 2 decimal places and I'll be happy. And then if I go switch gears then to figure out what angle B is, what trig function would I use to find B? Cosine, because you want to reuse your givens, because you don't, in case you screwed this up. And then you go through that route. I know that I already put problems on the calendar.
I didn't see those.
I thought I put them on there, didn't I?
During my study hall 6-7.
Oh, then I didn't do it. So let me pull those up real quick. Sorry about that. I thought I did. Oh, it was for geometry. I did that. We'll do more of the elevation depression stuff tomorrow. Today is just kind of a quick run through. Do those, please. These two sets here. This is what we're going to talk about tomorrow. How do we find sine of an angle given the tangent of an angle and work out of that? What's up?
Look, right?
Yeah, I saw the old book stuff. Yeah. So do these sets of stuff for tonight. Tomorrow we'll talk about how we do this and angles of elevation and depression. Okay. It's a lot of quick action right off the bat today, so it's good fun.
Just have hair that looks like